Hello, today we're going to look at alternating series. Okay, so alternating series are a pretty simple variety of series. So here's a couple of examples. So the alternating refers to the sign of the term. So if we look at the top here, minus 1 plus 1, minus 1 plus 1, minus 1 plus 1, that's clearly alternating. And generally the series will look something like that. I've thrown another little one in here, the sum from n equals 1 to infinity of cosine n pi. But in fact, if you start figuring those out, cosine pi, cosine 2 pi, cosine 3 pi, I think you'll find it looks just the same as the one above. In general, our alternating series will have some sort of form like this, with a minus 1 to the n, or a minus 1 to the n plus 1. And we saw this with sequences previously. All this minus 1 to the n or the n plus 1 does is alternate the sign, making it plus minus, depending on whether the n is odd or even. And the only difference really between these starting with the n or the n plus 1 is whether you start with a negative 1 or a plus 1. So you can see these two series are essentially the same, except the top one here starts with a negative 1 because this power is n. And the bottom one here starts with a positive 1 because the power is n plus 1. So these are a few examples of alternating series. We'll go on to our more formal definition of an alternating series. So we're going to let the a-n's be positive here. That's important because if they're not positive, it doesn't quite work the same with the negative 1 here. So the a-n's are positive, and then we put the negative 1 to the n or the negative 1 to the n plus 1 in front, and these are both alternating series. And the wonderful thing with alternating series, we have a really quite simple test for whether a series is converging or diverging. And it goes like this. If the limit of the terms is approaching 0, then the alternating series converges. And that's pretty simple. All we need is that the terms go to 0, and then the series itself will converge. Okay, so let's take a couple of examples of converging alternating series. Okay, this is the one we just saw, minus 1 to the n multiplied by 1 over n. Clearly, as n goes to infinity, 1 over n goes to 0, so this would converge. This one may be slightly more complicated, but not much. Again, we have the minus 1 this time to the n plus 1 here, so it's alternating, and then the root n over n plus 2 also goes to 0 as n goes to infinity. And finally, again, this one looks slightly more complicated, but again, hopefully you can see, even though the minus 1 is sort of inside with the other pieces, it's still alternating just as the previous ones are. And as n goes to infinity, the term is going to 0, so that would also be a convergent alternating series. So there's 3 examples that we can very quickly and easily see are convergent. Along with alternating series, we have the alternating series test, which tests whether something is absolutely convergent or conditionally convergent. Part 1 here says that a series converges absolutely if we take the absolute value of all the terms, which essentially means getting rid of all those minuses. If that converges, then the series also converges, and we call it absolutely convergent. Whereas part 2 says it converges conditionally if the series itself, so the alternating series, converges, but if we take the absolute value here, that diverges. So if the series itself converges, but the absolute value of the terms gives us a series that diverges, then we call it conditionally convergent. And we'll take a couple of examples to see how that might work. Okay, so let's take the alternating harmonic series. So we've seen the harmonic series in the past, which is just the sum from n equals 1 to infinity of 1 over n. Now we throw that negative 1 to the n at the front. Okay, and well, let's take the absolute value. Let's consider the series with the absolute value, in other words, throwing away that negative 1 at the front. Well, we know from what we know about the harmonic series that in fact diverges. The sum from n equals 1 to infinity, 1 over n diverges. However, if we take it with the negative 1 still in place, from what we saw just a moment ago about when an alternating series converges, that would converge by the alternating series test. The terms are going to 0, so it converges. So this original alternating harmonic series we have at the beginning here is called conditionally convergent. It converges, but the absolute value diverges, so it's conditionally convergent. Now we'll take an alternating geometric series. The ratio here is 1/2. You can see 1/2 to the n, or 1 over 2 to the m. Again, it's alternating because of the minus 1 to the n. Again, if we take the absolute value here, well, it still converges. Okay, it's a geometric series with the absolute value of r less than 1, therefore this converges. And similarly, if we take the same thing but with a negative 1 in the front, that still converges. And actually we could look at that two ways. Just as a geometric series it converges with r equal to negative 1/2. But we could also take a look at the alternating series test and say, well, the term's going to 0, therefore it converges. Because it converges and its absolute value converges, we can call that absolutely convergent. It's an absolutely convergent series. Since we looked at some absolutely and conditionally convergent, maybe we just look at one of the type. We can also look at a divergent alternating series. So here we have -1 to the n plus 1 times by n, and it's very easy to see if we just take the terms. We get 1 minus 2 plus 3, and there's no way that that's going to converge. So that's a divergent series. That's another example. If we have -1 to the n of n over 3n plus 1, well, if we take the limit as n goes to infinity of n over 3n plus 1, that actually equals a third. And since that equals a third, we know that the terms are not going to 0, and that was our original test for convergence. So the terms are not going to 0, it cannot converge. And in fact, that brings us on to a little reminder. Okay, at this point, I just want to bring together a couple of the theorems we've seen. Okay, so if the terms go to 0 of some sequence, then if it's alternating series, then the series definitely converges. However, if it's not an alternating series, this simply says it may converge. It's got a chance. Okay, it's very tempting at this point to say, oh, well, the term's going to 0, it converges. That's only true if we have this alternating series. Okay, so that's everything on alternating series.